without reasoning with other people there, and they just hold their view, and then they try to impose their view to everyone else. So stay away from those radicals there. Okay, so these are the exceptions to the octet group. Sometimes you can have fewer than 8, sometimes you can have more than 8. Now, in the situation where you have more than 8, and that only happens to the elements on the third period or higher, when you have a large hotel and extra rooms there where the more electrons can be accommodated. And then another situation is when you end up with odd number of total number of valence electrons. When you end up with an odd number, then we end up with free radicals. So these are the 3 exceptions. These are the only 3 exceptions to the octet group. And pretty much everything else, when you try to draw a Lewis structure, everything else will follow the octet group. And you just try to draw out the correct skeletal structure of the molecule and count the total number of valence electrons, and then distribute the electrons according to the octet group. But every time and you see things that go beyond the octet group, and these are the exceptions there. Okay, so that's pretty much about the topic that we want to talk about in terms of drawing a Lewis structure there. Okay, and now another situation there, since we're on the topic of drawing Lewis structure, another situation is that when we have double bound or triple bound, when we have multiple bounds, there is a possibility that you may end up with more than one Lewis structure, and you will always argue in that case which one is correct. I'm giving you an example here. Okay? If you have ozone molecule, O3, if you count the total number of atoms and total number of valence electrons available among the 3 oxygen atoms there, this would be a Lewis structure that these would be Lewis structures that you will come up with. So one situation is you have the double bound between the 2 oxygen on the left side, the other is on the right side. Now, if you measure the bound length in the laboratory, we know that in this case, if you have oxygen-oxygen double bound, individual oxygen-oxygen double bound, the bound length should be somewhere around 121 picometer. Okay? When you have an oxygen-oxygen single bound, it's going to be somewhere around 132 picometer. Now, what happens to ozone? You have a double bound in there, you have a single bound in there. Okay? Now, when you measure the bound length of ozone molecule, you don't get 121, you don't get 132. As a result, you actually get 127.8. All bounds, all the chemical bounds in the ozone molecule are equivalent to one another. They have a bound length of 127.8. So this indicates we do not have a fixed situation of single bound and double bound, either on the left or on the right side, within the molecule. So this is the situation where the scientists have to come up with an explanation. We don't know the actual situation in there. Based on the Lewis structure, well, we have a double bound, we have a single bound, connected to the same atom in the center, the oxygen atom there. Now, based on the O theory and things that we already know, and these 2 different types of bounds are supposed to be different from one another, but when you measure the bound length, they happens to be identical. How do you explain that? Well, we use what we call the resonance theory. Okay, so the separate Lewis structure in this case does not represent the actual reality of the molecule there. It's actually the molecule itself is a composite of both structures there. Meaning the double bound, the position of the double bound in this molecule is moving very rapidly between among the 3 oxygen atoms that we have here. At one moment it's on the left, and the other moment it's going to be on the right. Okay, so the electrons that the electrons that made up of the pi bound, what we call it pi bound there, the double bound there, okay, that electron can be delocalized from one location to another, but they're moving at a very fast speed. So the actual structure of ozone molecule is a composite of the 2 possible Lewis structures there. And a single Lewis structure does not represent the reality there. How do you understand the resonance situation? It's like a hybrid. Okay, so the double bound is moving, and when you have 2 different breeds of dogs there, their offspring bears the characteristics of both parents there. Okay, so in this case, we can say that the double bound on the left and the double bound on the right, these are the 2 different breeds there. And the resulting ozone molecule is a composite, is a combination of both molecules in there. So we use a dotted line to represent that double bond. A dotted line on the left, dotted line on the right, and join them at the same time, meaning those electrons, the electrons that are responsible for forming the double bond on the left or on the right, they can delocalize from one position to another. But that motion is very rapid. We will not be able to differentiate between when do you have the single band, when do you have the double band. So when you measure, when you do a measurement in the laboratory there, you end up with the same bond length there. So this is the essence of the resonance there. The electrons that are responsible for forming multiple bonds, whether double or triple. Those electrons can delocalize and then move very rapidly in between two adjacent atoms there. So this is what we call resonance. Now resonance is a very important theory in organic chemistry, because many organic compounds, they have double bound or they have triple bonds in there. And that makes them reactive. The reactive site in the molecule is where the double bound and triple bonds are. So the resonance structure there, for example, if you do a carbonate ion, when you draw a carbonate ion Lewis structure, you can come up with as many as 3 Lewis structures. Now which one is correct? All 3 are correct. How do you represent them? You use a double-headed arrow. Okay, so this is the carbonate ion where the double bound is on the left side, and this is the carbonate ion with the double bound in the center, and then this is the carbonate ion with the double bound on the right side. Each one of them is a partial representation of the Lewis structure for the carbonate ion. All 3 of them coexist. So all 3 actual structure is a composite of 3 resonance structures. Now what's the importance here? In organic chemistry, when we try to conduct organic reactions there, now sometimes you may end up with, especially when the compounds are involves a double bound, when the product involves the double bound there. Now sometimes you end up with a majority of one particular type of chemical. Sometimes you end up with the, from an organic reaction, you end up with the one particular type of, another particular type of structure there. What determines what's going to be the major product of a chemical reaction? Now, in organic reactions there, if you end up with a product, and if you can have more resonance structure for that product, well, that is said to be more stable, as a more stable product there, and you should be able to generate that product in larger quantity. So this is used in addition, the resonance structure, resonance theory is being used to make predictions about one of the applications there. Anyway, is that we can use resonance structure, resonance theory to make predictions about organic reactions. We will be able to predict, and based on this particular type of structure, well, this is going to be the major product. So organic chemical reactions there is not like a clear-cut thing like in the inorganic chemical reactions there. You mix these 2, these are the compounds you're going to get. Well, you mix these 2 in organic chemistry, and you mix these 2 organic compounds together, well, you may get, say, 80% as these products and 20% of the other. So the resonance structure basically indicates how do we explain different types of structures there. And you could have a majority, a major product, or a minor product there because of the resonance structure. Okay.